Now let's consider a scenario where we have some friction force. So once again we have an external force F acting on our object, causing a displacement delta S along the S direction. That's our S direction, and which gives rise to some change in the kinetic energy of the object, which we can see just doing a similar analysis to what we did in the first part. But now there is some friction force, and the friction force here, little f, is in the opposite direction to displacement of the object, of course. So that's final. So now we can show that the change in the kinetic energy is equal to the integral of f ds over the displacement, and integral of the friction force ds over the displacement. And thus first integral we define as the work done by external force F, and and this integral here, following similarity in the form of the equation, is what we define as the work done by friction force. After all, we have a force which is which is integrated along the displacement from SI to SF. So that's work done by friction force. And if we recall, what we had said earlier was that work done by external force was equal to change in kinetic energy of the object plus a change in the thermal energy of the object, of course, plus change in the in the potential energy of the object as well. But in this case, since displacement is along the horizontal, this is 0. So this means that work done by friction force is equal to the negative of the change in the thermal energy of the system. So that's an important relationship to bear in mind. Now let us take a look at the situation where we also have a change in the potential energy of the system. So let's say an object slides down an incline of angle theta. Once again, the forces acting on the system are mg, weight, an external force F along, let's say, the horizontal, and friction force which acts in the opposite direction to the displacement of the object. Our displacement again is delta S along the S direction. So this is our delta S, the displacement. And our object goes from initial velocity to some final velocity. Doing a similar analysis, you can show that this change in the kinetic energy is equal to work done by external force F, but do remember that it's the parallel component. This is a dot product here, so it's a parallel component of F along displacement that you need to integrate. And work done by the friction force, which is work done by our non-conservative force, and work done by mg dot ds. Mg is the force due to gravity, and therefore this here is the same form as what we define work to be. So this we can call the work done by our conservative forces, and that so work done by external force plus work done by non-conservative forces plus work done by conservative forces equals change in the kinetic energy of the system. And just like before, we can assign an energy term to these works. So work done by non-conservative forces, we said, is equal to negative of the change in thermal energy, and work done by conservative forces, the change in the potential energy due to that force. So rewriting this equation, we have work done by external forces is equal to change in kinetic energy, which is the term we had up there, plus change in potential energy, plus change in thermal energy. And if we had not just changing gravitational potential energy, but we also had some spring forces in the system, such that in addition to gravitational potential energy, we also had some changes in the spring potential energy involved, then the expression takes a more general form, which states that the work done by external force on the system is equal to change in kinetic plus change in gravitational potential plus change in spring potential plus change in E thermal. Now, it's a good idea in problem solving to start with this general form and then ask yourselves, is there an external force acting on the system? And if the answer is no, then this term becomes zero. And ask yourselves, is there any friction forces involved? If the answer is no, then this term becomes zero. Then is there any spring force involved, or is there a change, is there any spring force involved? Is there any change in the spring potential energy? If the answer is no, the spring force is zero, then this term becomes zero. So gradually you see that you end up with the very early form of conservation of mechanical energy that we had, delta K plus delta UG is equal to zero. So, and if you recall, we had assumed in driving that we had assumed that external forces were zero and friction were zero. So it's a good idea to start with this general form where you have all the terms that one would care about, and then eliminate them depending on whether or not external forces exist, friction exists, and what type of potential energy you're dealing with. A little bit more on work done by weight, what we have here is the general statement for definition of work done by any force F is the integral from the initial position to final position of this term, which is F dot ds. Now this is a vector dot product, so if in the case of our object M sliding down the slope, the object starts at a height h, so here y equals h and here y equals 0. Obviously we have a change in the gravitational potential energy. I'm going to define 0 level my reference level for gravitational potential energy. That's my UG 0 level. So at my initial position, gravitational potential energy that the object possesses is mgh. Now what are the forces acting on the object? Let's assume friction is non-existent, so there's no friction. The only force on the object is mg, and it's directly downwards. The displacement delta S is of course along the slope, so the component of force along the displacement of the object, mgs, is given by mg cosine theta, where theta is the angle between the force and the displacement vectors. Okay, so this integral of mg dot ds, when you evaluate it, it's equal to mg cosine theta times delta s, where delta s is s final minus si, the total displacement for the object. Now h, you can delta s times cosine theta is equal to h. You can see that by simple trigonometry, and this term here of course is defined as work done by mg. So substituting in h for delta S cosine theta, we'll have work done by mg is equal to mgh. But what is the change in potential energy of the system? So change in UG is equal. We went from our final potential energy down here is 0, of course, minus our initial, which was mgh. Therefore, change in the gravitational potential energy is minus mgh, which means that work done by mg is equal to negative of the change in the potential energy due to that force, or the negative of the change in the gravitational potential energy. So in short, work done by conservative forces such as spring force or gravitational force is equal to negative of the change in that potential energy. So work done by mg is equal to negative of the change by ug, and work done by spring force is equal to negative of the change in the potential energy due to spring potential energy, and work done by non-conservative forces such as friction force is equal to negative of the change in the thermal energy. Now, a couple more words about these conservative and non-conservative forces. Now, work done by change in the gravitational potential energy only depends on the displacement, the vertical displacement of the object. So if an object starts at this initial position, ends up in this final position down the slope, if it whether it took the straight blue path or the wavy red path, the change in the gravitational potential energy, delta UG, only depends on delta Y, change in the height of the object. It is path independent. However, the change in the thermal energy of the system, let's say there is friction forces are non-zero, is very much path dependent. Therefore, whether the object takes the blue path or the red path will matter. So work done by non-conservative forces such as friction depends on the path taken. So but work done by conservative forces is path independent. It only depends on well, in the case of gravitational potential energy, only change in the position, the vertical position of the object. Now, if the force being applied to the object which causes the displacement is not constant, and as I said, you have to resort to integral techniques. For the purpose of this course, we don't use so much integration, but we use the concept of area under a curve. So if you know that the force along the x direction applied to an object is given by this graph here. So this is the force along the x direction, which causes, of course, a displacement along the x direction. Then the work done by Fx is the area under this curve. So work done, let's say from 1 second to 3 seconds is the area under this triangle, which is 1/2 of the height of the triangle times the base, so 1/2 times 10 times 2, which is equal to 10 joules. So that's the work done from, also did I say seconds? I meant meters. So work done to move the object from, displace the object from 1 meters to 3 meters is 10 joules worth of work. Now, work done to further from 3 meters to 4 meters here, well, the area here is negative, so that's a negative work. So if you were to consider the work done by Fx all the way from 1 meter to 4 meters, then you have 10 joules worth of work for the positive area up there, and you have, let's say if this were 2 for example, then you have minus 1 joule of negative work for the area down here, which is a total of 9 joules of work being done on the object. Now this 9 joules of work being done means the kinetic change in the kinetic energy of the object is 9 joules, i.e. it's a positive number, which means that as a result of this total work applied to the object, our object actually speeds up. The kinetic energy increases. If the net work done on the object by this force had turned out to be a negative number, then delta K would have been negative, which would have implied that the object actually slowed down. So the important relationships to remember are that if the force is constant, which causes a displacement, the work done by that force is the dot product of F delta S, or the product of the parallel component of F with the amount of displacement. Work energy theorem states that delta K, change in kinetic energy, is equal to the net work done on the object. This is very, very important. Please do make a note of it. Work done, its change in kinetic energy is equal to work done by external forces plus work done by non-conservative forces plus work done by conservative forces. So this whole thing is the net work done on the object. And if you have if you don't have a constant force acting on the object, you have to consider the integral or the area under the curve. Area under the curve. This is F versus this position curve to calculate the work done on the force. So allow me to ask you to think about this question here. We have an object which is undergoing circular motion with an angular velocity omega. The object is attached to a string, so there's a tension T in the string. And the question is, what is the work done by tension? What is the work done by tension? Is it A, B, C, D? If you like to think about this for a second, if you like to put the video on pause and think about it, you can come back to it. So work done by tension. So tension, of course, we know is along the radial direction, and the displacement of the object at any time is along the tangential direction. And radial direction and tangential direction are of course perpendicular to each other, so at any given position the tension dot delta S is 0, because the cosine of 90 degrees is equal to 0. So because the force, the tension and the displacement at any given time are at 90 degrees to each other, the correct answer of course is B, which is 0. So work done by tension in this case is 0. Similarly, well, not similarly, this is a different question. If you like to think about this too, I have two objects, a 1 kilogram object and a 10 kilogram object, and I apply a constant force F to either object over a distance L. It's a fixed distance L. At the end of this displacement L, my first object has a kinetic energy K1 and second object has kinetic energy K10. So this is 1/2 of mass 1 times velocity 1 squared, and this is 1/2 of mass of the 10 kilogram object times velocity of the 10 kilogram object squared. So the question is which object has a greater kinetic energy? So um, which one of these relationships are true? If you'd like to think about that and then come back to the video, I'll share the answer with you. What you'll need to consider here is that change in the kinetic energy of the object. By the way, here perhaps I forgot to mention, both objects starts at rest. So velocity initials are 0, so both objects start at rest. So change in kinetic energy of the object is equal to work done, net work done excuse me, net work done on the object. Here the only force to consider is that we need to consider is F, our external force, and work done by F is simply F times L, because the direction of our displacement and force are parallel to each other. So you notice that the change in the kinetic energy of whether it's the 1 kilogram or the 10 kilogram object, they're both equal. Because I said it's a constant force F in either case, and our displacement is L for either case. So change in the kinetic energies are equal. Both objects start from initial kinetic energy of 0, which means the final kinetic energies are equal to each other. So Kf of the 1 kilogram object is equal to K final of the 10 kilogram object, which means that C is the correct answer. And finally, if you would consider this scenario, we have force along, I should say Fx, force along the x direction given by this by this graph, and this is displacement along the x direction, and the object at x equals 0 meters has a velocity of 2 meters per second, let's say, and question is regarding the velocity of the object at x equals 5 meters. Is it greater than velocity at 0? Is it less than velocity at 0? Is it equal to 0? Or are the two velocities equal? So once again, here we have a case where the force is not constant, or the display or the period or the object is being displaced. Therefore, you need to take a look at the area under the curve. We are comparing velocity at 0 meters to velocity at 5 meters. The area under the curve is the positive area here, which is 2 times 2, so this is 4 joules, and the negative area here, which is 1, 2, this is 1 joule. Therefore, net work net done on the object by Fy is equal to, actually I should really call that work by Fx is equal to 3 joules. That's a positive amount of work being done, which implies that the change in the kinetic energy of the object is 3 joules, i.e. the object speeds up, which means that velocity at 5 meters is greater than the velocity at 0 meters. Now, let's do this. We know that, well, the object had initial velocity, the 2 meters per second velocity at x equals 0 meters. So delta k, which is equal to k final minus k initial, is equal to 1/2 of mass times velocity at 5 meters squared minus 1/2 of mass times velocity at 0 meters squared, which is equal to 1/2 of mass. Now velocity at 5 meters we don't know, squared, minus, but we do know the velocity at 0 meters, which was 2, which is 2 squared, and this whole thing must equal 3. So now you can solve this equation for V5, so you can figure out what the velocity is at 5 meters. So to do that, you also need to know the mass of the object, but the problem will give you the mass of the object. So just wanted to share this quick example with you.